And we should be good to go. Recording for everyone who is watching later. Welcome if you're watching later. So basically thank you for that last ID. Basically the way that this works is you guys can come in. You can come in with questions. You can come in just kind of wanting to do some practice problems. And we're just going to kind of walk through like what we covered this week and chat about how to kind of solve problems. So this is a guided study group, so it will be wonderful if you guys can kind of contribute, whether through the chat or if you want to hop on the voice channel. That would be spectacular. And yeah, that's basically the intro to this, how this kind of works. Why don't we go ahead and get started? All right. So let's start ourselves in chapter 1. This week you guys covered sections 1.8, 2.1, and 2.2, right? And I just want to clarify because sometimes I do mix up the weeks and I come completely like with the wrong week prepared, which is always like the worst. And it's really bad when I start going off and like doing it and nobody tells me. So awesome, we're doing the right sections. Spectacular. So I am currently on page 91 in the book. And so I'm in section 1.8, which is continuity. Let's go ahead and start with problem 3 to take a look at where stuff is continuous and where it isn't continuous. Do you guys all have your book with you? If not, I can go ahead and sketch something out. So what about, where are some places that we think on this graph in problem 3 where F is discontinuous? And why? Okay, so why do you think, yep, there's a hole there at -4. And why at -2? There's a jump. Another way that we can kind of say that is that oh no, that's fine. I also have the ebook, which is why this is at half. I'm trying to get my hands on a actual physical book this year so that I can have like the full screen to work with. So yeah, and the last one is going to be, or the last couple are going to be x is equal to 2 and x is equal to 4. Sweet. And the reasons for these are like the same in principle in that this at x is equal to 2 is a jump. And at x equals to positive, x is equal to +4, it's also a jump, as it's going to infinity at the asymptote. The limits are not the same. If you're coming in from the left, it's going to be going to -infinity, and if you're coming in from the right, the limit is going to be some number on the y-axis, some number. So we're going to call that a jump too. All right, so that's pretty clear. It's probably pretty easy to see like where things are with graphs. So let's move on and do let's do problem 9. So the toll T charged for driving on a certain stretch of a toll road is $5, except during rush hours, which is between 5 a.m. and 10 a.m. and between 4 p.m. and 7 p.m. And the toll is $7. So sketch a graph of T as a function of time, where T is measured in hours past midnight. And then discuss the discontinuities of this function and the significance to somebody who uses the road. So I'm going to go ahead and set up a graph here. I can say that in hours past midnight, so this halfway point is going to be 12 noon. This is going to be 24, so this is going to be midnight. That means that this is going to be 18, which is going to be about 6 p.m. So here is going to be, we'll call that 19, and we'll call this is going to be 16. So this is going to be 4 p.m. and this is 7 p.m. here. And then here will be 10 a.m. and here will be, it's probably about halfway, so that's 6, and then here could be 7. And I just kind of wanted to set up some like points along here that we can use. Okay, so we are going to have a toll that is, this is going to be our y-axis, is going to be cost or toll. And we have two values that it's going to be. We have $5 and we have a $7 toll. So from midnight until 7 a.m., this toll is going to be $5. It's going to be flatline. And then am I going to have an open circle here or a closed circle? Yep, open. And my closed circle is going to be where? It's going to be up at 7. So I'm going to have a closed circle up here, and then I'm going to go to 10 a.m. I'm going to kind of repeat. I'm going to have an open circle at 10, and that's when it makes the switch back down to $5. We're going until 4. And then back up to $7. Go to 7 p.m. and then from midnight onward, I'm going to end with a closed dot because I'm not like creating something that's kind of cyclic. I'm just looking at like one 24-hour period. So yeah, so this is kind of what this graph is going to look like. And we can see pretty clearly where it's discontinuous, where there is like a huge jump. What does this kind of mean for someone who uses the road? I think this is kind of a bad part of the question. The significance for someone who uses the road is just going to kind of be to avoid the road during like prime time, because it's more expensive that way. And then this, as soon as it ticks over to 10 a.m., for instance, then you're back down. So if you're going to go through a toll booth, you want to go through at 10, not at 9:59 a.m. So yeah, so we have a couple of continuous parts of this graph. Okay, any questions about kind of looking at this graphically? All right, let's do problem 11 then next. And so this is looking at a little bit more of an like algebraic approach. So, oh shoot, lost my page. I'm so sorry. This is what happens with the, okay. This is, okay. All right, so problem 11. we have this function, which is f of x is equal to x plus 2x cubed to the fourth, and we have a is equal to -1. So we are going to use the definition of continuity, and we're going to use the property of limits to show that the function is continuous at this number that we're given, which is a is equal to -1. So where am I going to start? Yes, so that is going to be my definition of continuity. I'm going to check, number one, that A is in the domain of f. I'm going to check that, or f of x, as you put it, that f of a and the limit of a exist. And yeah, the limit as x goes to a. And then that these limits limit of f of x as x goes to a is equal to f of a. So yeah, this is kind of where we're at right now. We can start off just by checking to make sure that f of a exists. We can just do that by plugging in -1 here. So this would be f of -1 is equal to -1 plus 2 times -1 cubed to the fourth. So this would be -1 minus 2 to the fourth, -3 to the fourth. So that would be just 3 to the fourth, which is 27 times 3. Sorry, I should have this memorized, but I don't. So 81. Yeah, duh. Okay. Yeah. So now we know that A is in fact in the domain of f, and we know that f of A is equal to 81. So if we know that f of A is equal to 81, what we need to determine is, number one, that the limit of A as x goes to A does exist, and that the limit is equal to 81. So how am I going to start going about evaluating that? Since A is in the domain, we can use direct substitution. Yes. So what is this going to kind of look like? We'll start with the limit as x goes to A of x plus 2x cubed to the fourth. So how are we going to start solving this limit? Oh, and you said use substitution, so put this in as A. And you want, is this kind of what you're referring to? Awesome. And then A is going to be approaching. Sweet. So what's happening here? So if A is approaching, we should definitely take this both from the left and from the right, just so that we know we're like working through this right. So we're going to do this from, get the notation for this, I'm sorry. So we're just going to say that this is from the right, and this is going to be from the left. I think like a plus afterward or something. Sorry, it's the beginning of the semester for me too. So from the right, this is approaching -1 plus 2 times -1 from the right, and then it's all going to be to the fourth. So that'll be -1, this is cubed, sorry, plus -2 to the fourth. And it really doesn't matter if we're taking it from the left or from the right for this instance. It does matter in other instances, as I'm sure you guys have covered. But from here, from the left and right, it's going to be the same. And we're going to end up with the limit as a approaches -1 is going to be is equal to 81. So now that we've said that, we have our limit, and we have that that is equal to also f of a. So we have confirmed that yes, this function is continuous on this at this like number. So yeah. Any questions about what just kind of happened? Okay. Let's do another one of these. Let's do number 13. So here we're going to have p of b is equal to 2 root 3b squared plus 1, and a is equal to 1. So we're looking for f of a exists. F of a, or okay, what was it? It was f of a is defined, then as x approaches a of f of x exists, and then those two are equal. Okay. No. Sorry, I just looked at the chat box and I saw the word no. I probably asked if somebody had any questions and somebody said no. I just want to clarify that somebody isn't saying no to something that I'm writing down right now. I'm so sorry. Okay, all right. So back to this. We start off by confirming that f of a exists by saying this is p of a, which is p of 1, which is equal to 2 times 3, or 2 times the square root of 3 times 1 squared plus 1, which will be 2 times 3 times 1 is 3 plus 1 is going to be 4. So this will be 2 times 2, which is equal to 4. So f of a exists, and it is equal to 4. Or rather, p of 1. All right, so now we go back around to this limit. So we're going to have the limit as x goes to a of this quantity. It's not going to be x, it's going to be b goes to a. 2, 3b squared plus 1. As we did in the other problem, we can use the substitution here to say that this is the limit as a goes to 1 of 2, 3a squared plus 1. And we can go ahead and say that if a is approaching 1, then 3 times a squared will be approaching 3. Then that whole thing under the square root sign will be approaching 4, which means that the square root sign is going to be approaching, this is going to end up being 2 times the 2, what is approaching 2. So this limit is going to be equal to 4. And there we have it. 4 is equal to f of a, and 4 is equal to the limit as x approaches a. All right. Let's see. Let's also do, let's do problem 15. So here we have the function f of x is equal to x plus the square root x minus 4 on the interval 4 to infinity. Okay. So, what are we looking at here? We are trying to use the definition of continuity and limits to show that this function is continuous on this interval. Where am I going to start? Yeah, so I'm going to set up this. I'm going to set up this limit. I'm going to say that the limit of f of x as x approaches a is going to be equal to the limit of x approaches a. This is going to be x plus root x minus 4. I am going to, so you said approach 4 from the right, so you want to say that x is approaching 4 from the right? Such as, let's see. That looks like this, right? Sorry, it's been a hot sec. So yeah. Okay. So if x is approaching 4 from the right, we have this is approaching 4 minus 4, but it's approaching it from the right, so it'll be positive, which means that we're approaching the square root of 0. And this is also approaching 4 from the right, correct? So I could say that this is x minus 4 is approaching 0 from the right, which means that the square root of 0 from the right is approaching 0. And then this will end up being 4 plus 0. So this limit is going to be equal to 4. So what does that tell us? Well, let's also, yes, so the limit is equal to 4 when we're approaching 4 from the right. But let's also take a quick look at what happens if we approach it from the left. And that is, oh, I gotta hold a second. Yeah, you don't have to apologize for being wordy. This is good, but you're exactly right. You're exactly right. So we would get a limit if we approach this from the left as like this would not exist. So this doesn't exist. But as you said in the chat, we aren't concerned with approaching it from the left because it isn't on the interval that we're checking. Although, is it? We have a bracket there instead of a parentheses. So yeah, so we don't have a limit at 4 itself. We because we have this disjointed, we have a limit that doesn't exist versus one that does when we approach it from the left and from the right. Okay, so as you said, we're approaching it. Limit approaches from the right exists. So any limit on that interval also exists. You're right. So we can say that because we're approaching it from the right, and this limit is like in existence, we can say that f is continuous from the right at 4. And it looks like this should exist. So I'm gonna, I guess this might be a notation issue, but regardless, this does exist on this interval. This is correct. So we have proven continuity. Sorry that I'm like getting a little muddled in trying to explain this. So yeah, let's also just like explicitly state that we are using like the definition of continuity. So again, we have to consider what f of a is equal to. And in this case, a is going to be equal to 4. And so we just wanted to make sure that f of 4 is equal to 4, which it is, rather if we take 4 from the right and not from just like the number or from the left. Because this is weird. I'm sorry. I'm reading 2 things that are a little disjointed. The function is not continuous at 4, at the number 4, right? My notes are saying something different than what I'm seeing online right now. Like, I'm looking at this and I'm like, that doesn't seem right. Why did I write this down? Okay. If anyone has any input, of course, like this is kind of like a problem solving venture and like us trying to figure this out. So like, feel free to jump in at any time. So we want to use, like we definitely are trying to use like the rules of continuity to prove that it's continuous on this interval. If it is continuous, okay, so a function f is continuous on an interval if it is continuous at every number in the interval, right? If f is defined on only one side of an endpoint on the interval, we understand that it is continuous at the endpoint to mean continuous from the right or continuous from the left. So that's what's going on here. The number f of a doesn't exist here. And then the limit is not continuous from the left, but it is from the right. And that's what we care about. So we can say that this function is continuous on that interval. Okay. Let's move on to section 2.1, where we're going to be talking about derivatives and rate of change. Unless anyone has any other questions about the continuity stuff. So let's start with number let's see what page this is on. This is on page 113. And we're in section 2.2, which is derivatives and rate of change. So let's track down. Okay. All right, so let's do problem 5. So we're finding an equation of the tangent line to the curve at the given point. So I'm kind of being like tasked with tracking down the derivative, and the method that we have to do that right now is by using the slope of the tangent line, which we're going to call m, is going to be equal to the limit as x approaches a, f of x minus f of a over x minus a. You guys, I'm sure I said that. All right, so where am I going to go after this? What's my next move? If I'm trying to find the equation of the tangent line to the curve. Plug in the formula and A. What formula am I plugging in? Yes. Okay. So I am going to use x is equal to 2 because I've been given this point. Sorry, I totally didn't write down the equation. So our equation that we're looking at is y is equal to 4x minus 3x squared on the point to negative 4. So I'm going to use x is equal to 2. I'm going to find out that y is equal to 8 minus 12, so negative 4, which is exactly like what we have. So f of a is going to be equal to y, our y value. And so m is going to be limit as x approaches negative, or x approaches 2, because this is going to be our a. And yeah, so f of x is going to be 4x minus 3x squared minus f of a, which is going to be 4, and then x minus a, which is going to be 2. Okay, so we've got this in these terms right now. And sorry. Okay, so this is going to be the limit as x approaches 2. We can, let's see, let's rearrange this a little bit. So we have negative 3x squared plus 4x plus 4 over x minus 2. We can turn this into this. Can be what? Negative 3x. To be negative 3x minus 2x minus 2. It'll be negative 3x squared minus 2x plus 6x plus 4. So yeah, this can be turned into then the limit of x goes to 2 of negative 3x minus 2 times x minus 2 over x minus 2, which means that we can get these to cancel. This is going to be equal to x minus 2. And now we can say as x approaches 2, what is going to happen? So as x approaches 2, negative 3x is going to approach negative 6, and this whole thing is going to approach negative 8. Okay, so we're sitting where we are. X is going to be equal to negative 8. What does this give us? And what are we trying to find? Yeah, this is m. I probably said x in there, and I'm sorry, so this is going to be m. And what we're trying to find is a tangent line. And probably the form y is equal to mx plus b. And what we're given is we're given this point, and we're given this slope, so exactly what you just put in the chat box. Y is going to be minus negative 4 is equal to negative 8, x minus 2, which we can rearrange into being did I miss? This should be 12, yeah. So this is going to be our tangent line equation for this function at this point. Sweet. Okay, any questions about that? So I was going to do problem 9, but that's pretty much the same thing. So instead, let's look at problem 11. Okay. So we're looking at this graph, and we're saying that a particle starts to move to the right along a horizontal line. The graph of its position function is shown in the figure. When is the particle moving to the right? When is it moving to the left? When is it standing still? And then draw a graph of the velocity function. So I'm going to kind of sketch out. I'm going to get 2 functions on this page. This first one is going to be the original function, which looks like this. All right. So when is the particle moving to the right? So it's moving to the right when m is positive and moving to the left when m is negative. Exactly. So from here to here, from 0 to 1, this is moving right. Then from 1 to 2, it is going to be standing still. From 2 to 3, this is going to be moving left. And then 3 to 4, we have standing still. And then finally, we are moving to the right from 4 to 6. Okay. So what is our graph of the velocity function going to look like? All right, so the slope from here to here is going to be 3. Can you like generally tell me like what your, yeah, exactly. So we're gonna kind of, if you remember like that toll booth kind of graph we had before, we're gonna be looking at something kind of similar to that in that, if I can set up 5, 6, and I need to extend this a little bit further. So we have it moving to the right from 0 to 1. We'll call this 3, and our velocity is going to be like this. And then what is our velocity going to be from 1 to 2 when it's still? Yes, it's going to be 0. So no velocity, no rate of change. When it's moving left, what is it going to be? -2. So this. And then we're back to being at 0. And then this last chunk. It is going to be, yep, that one. So this is the distance. So S of t, and then here is v of t. So yeah, open dots here. And you guys, just like, I know you know this, but I'm going to say it anyway. If you have S of t and you find the rate of change or the derivative of like the distance, you're going to end up with velocity. If you do that again, you're going to end up with an acceleration. And this is going to be used as an example a lot. And it's kind of just expected that you know that the like derivative of distance is going to be velocity, and the derivative of velocity is going to end up being acceleration. So yeah. All right. So let me clear all of this, and let's do one more problem from this section. Let's do problem 13. Let's do problem 13. So if a ball is thrown into the air with a velocity of 40 feet per second, its height in feet after t seconds is given by y is equal to 40t minus 16t squared. So find the velocity when t is equal to 2. So this is word problem time. So what do we know? Let's call this, we'll call it S of t is equal to 40t minus 16t squared. And we are trying to find the velocity when t is equal to 2. So let's kind of set this up. What are we looking at here? What is velocity going to be? Yeah. So we're going to actually set this up in a way that we're looking directly for the velocity of 2, or the velocity when t is equal to 2. So if v of t is going to be equal to S of t minus like S of a over t minus a, then what we're just going to say is this is going to be S of t is equal to, or S of t minus S of 2 over t minus 2. So we're like just looking exactly for the velocity at t is equal to 2. So, or rather, this is a limit. I'm so sorry, I missed that. I didn't include that. It's a limit. It's the limit of S of t. So ignore what I had written up there because that was also incorrect. There's no limit there. So this limit is going from t to 2 because our time is approaching 2 seconds. Okay, so now we can start putting stuff in that we know. For instance, this is going to be S of t, so we can say that this is the limit t goes to 2 of 40t minus 16t squared minus, and then S of 2. So we're going to have to go ahead and find that. S of 2 is equal to 40t minus 16t, 40 times 2 minus 16 times 4. So that would be minus 4, yep, 16. So this is going to be equal to positive 16. Yep, which you had right in the chat. So we're going to put positive 16 in here. So we're going to have minus 16 over t minus 2. Okay, so let's shift this around a little bit so it's a little bit easier to work with. We can say that this is the limit of negative 16t squared plus 40 minus 16 over t minus 2. Let's factor out the, we can factor out a negative 8, right? So that would put us at 2t squared minus 5 plus 2, minus 5t plus 2. I lost a t. T. And that's over t minus 2. So let's break this down even further. So this is 2t squared minus 5t plus 2. 2t plus 2. So this is t minus 2t minus 1. So we'll end up with negative 8 t minus 2 2t minus 1. That's right, right? Minus t minus 14. Sweet. Over t minus 2. So happy that we can cross those out. And that will leave us with a limit as t goes to 2 of negative 8 times 2t minus 1. And we can just go ahead and solve this. This is going to be, we have t approaches 2, so this approaches 4. Approaching 4 minus 1 will be approaching 5. No, that's adding 1. Minus 1 is going to be approaching 3. And then 3 times negative 8, we're going to end up with negative 24. So what we've done here is we've said that v of 2 is equal to negative 24. So what does this mean? Like, what are my units going to be for this answer? This is going to be 24 what? Feet per second, yeah. And what does that negative sign mean? Yep, exactly. So the ball is approaching the ground. It's falling. All right. So I think that should be okay for 2.1. If you guys don't have any more questions, we can go ahead and do a couple of problems from 2.2. This is just blew right past it. Okay. So, let's, for 33 for number, for 2.1 or 2.2? 2.1, okay, let me go back. Okay, so we're trying to find f prime of A, right? So here I am on page 114. Problem 33, we have f of t is equal to 2t plus 1 over t plus 3. All right, and we are trying to find f prime of A. Sorry. So where am I going to start? Yeah. Okay. And okay. So how am I going to use this to find what I need? Because I'm looking for f prime of A. So I'm looking for like a general experience right here. So how am I going to get what I want out of this equation? Okay. Okay, if I sub in A for t and don't take A out where I am right now, problem number 1 occurs here. If this is A minus A, then I've got 0. So one thing that like might indicate that we're not quite using the exact right equation here is that a lot of the times we'll use this if we know what A is, and we're like t is approaching some number, and that some number we can generalize to be A. Here, instead of t approaches A, what might be more useful is h approaches 0. Yeah, exactly. So we're going to use this other equation that allows us to find the limit with A as a variable instead of using like A as like pretending that we're going to just sub in a number, which we will. I mean, like that's like the point of using this, but like this will make it so we can solve this problem. Okay, so we're going to be using this equation. It's going to get messy. So buckle in. First things first, we're going to put this in as the limit as h goes to 0, and we're going to put in f of t. So it's going to be f of a, or not f of t, f of a plus h. So every location here, we're going, where we have t, we're going to have to put a plus h. So f 2a plus h plus 1 over a plus h plus 3 minus 2, and now we have f of a, we're just going to leave it as a, 2a plus 1 over a plus 3. And all of that is going to be over h. So what we can do here is, this is really grody. If we multiply by, if we just do 1 over h, and then 1 over h, right? We can do that. So that's essentially multiplying by 1. So 1 over h over 1 over h. And we'll multiply both by this. So we will end up with the limit as h goes to 0 of this is real gross. Should I do this? What I should do? I could just cross up there. I'm committed. Okay. Sorry, this is just gross algebra stuff. This is not like conceptual. This is me just trying to figure out how best to simplify this. Yeah. So that's going to be our bottom one right here. And then it's going to be minus 2a plus 1 over h times a plus 3. So this will be 2a plus h, or 2a plus 2h plus 1 over, I'm going to have to do this anyway. Okay. So this is going to be HA plus H squared plus 3H minus 2A plus 1 over HA plus 3H. Okay. I'm going to go back a little bit and do this a little differently, I think. Because what do I have to do here? I have to, okay, this is not what I want to do right here. What I want to do is multiply both of these by, or rather, I want to multiply both of these by 1. So this is going to be A plus H plus 3, A plus H plus 3, and this is going to be times A plus 3, right? So this is just multiplying by 1, but it's going to leave me with 2 times A plus H plus 1 times A plus 3 over A plus 3 times H times A plus H plus 3, and I can subtract these now because they have the same denominator. So I can say that this is minus 2A plus 1 A plus H plus 3. Yeah, I can do that. So we're back to simplifying. This will be oofda. 2a plus 2h plus 1 times a plus 3 minus 2 a plus 1. Okay. So this is going to this. Sorry. You can see that this is just algebra from here on out, right? We know what's happening here. We know what we're going to use. We are going to continue I can keep trying to simplify this. This is like the curse of like finding this by hand, is that it's really, really gross. Okay. Give me one second. Okay. All right. Let's try that then. Okay, so we have in the chat, Dan, I believe. So had an idea. So let's do, you said, so what did you end up doing?
Sorry, I'm just going to unmute it.
Yeah, go ahead. Yep, I can hear you.
So right here, just distribute the 2 to 2a plus h plus 1. Sorry.
Okay.
Minus, still in the same numerator, 2a minus 1.
Okay.
And then on the denominator, you have h in parentheses, and then in parentheses, a plus h plus 3. The 3 would be, I believe, outside. Sorry, I'm not looking at the book right now. I think it's just a plus h and then 3.
Okay, so are you where are you getting the h from? Did you do like this?
I have to look at the problem real quick. Sorry.
You're good.
So yeah, so that's just a product of that becoming a plus h plus 3 becomes the common denominator, and then you multiply it by h. Right? Am I messing something up here?
Well, we don't have an h here is the issue. And we can't just like tack one on by adding it into the denominator. We have to multiply it in.
I did that because it's divided, that whole numerator is divided by h. It's the same thing as multiplying it by 1 over h. So that's where I distributed the h in.
Okay, so did you multiply it by 1 over h like I did right here, or no?
Yeah, that's how I got the h in the front.
Okay, so shoot. Okay. So you did that 1 over h thing. I'm gonna go back just a little bit. So you ended up with 2a plus h plus 1 over h, a plus h plus 3. And you can like kill these because they are like they're extraneous. You don't need them. So you had 2a plus 1 over h, a plus 3. But like the issue is that there's like a plus h in here that is not in here.
Yeah, so I just started from the top, so I'm just doing it right now.
So this is incredibly annoying. I'm so sorry. Okay. Okay. So I think, sorry, I can write faster with like a pen, so I just like outlined a little bit more. This is gonna get real gross, but I think I've got something that works. So we're on the right track here. What we need to do is we need to, like we did earlier, we need to bring the same denominator into play. So we're gonna multiply both by, this is a plus 3. I think it does have to be this messy. That's like the nature of like this type of a problem. So we're going to end up with something that looks like this. We're going to have 2a plus 2h plus 1 times a plus 3 minus 2a plus 1 times a plus h plus 3 over the quantity h times a plus 3, and I'm going to start like distributing right now. So this will be a plus 3 times, because these are the same, so I can combine them. This will be a h plus h squared plus 3h, and I just distributed that h right there. And then I need to start distributing some more. So my next step, I'm going to say that this is going to be 2a squared plus 2ah plus a plus 6a plus 6h plus 3 minus 2a squared plus a plus 2ah. This is going to be in parentheses. 2ah plus h plus 6a plus 3. So I'm going to go through, I'm going to kill that parenthesis, and I'm going to distribute this minus sign, right? Because that's how I want to live my life. So I'm just going to distribute this minus sign to all of these. So this is going to be minus a, minus 2ah, minus h, minus 6a, and minus 3. And all of that is going to be over the quantity over the quantity a squared h plus ah squared plus 3ah plus 3ah plus 3h squared plus 9h. Okay. Do I want to do that? Yeah, I'm just gonna do it. So I'm gonna go through and cross out what actually, like, I can cross out here. Here I have a 2a squared, and here I have a minus 2a squared. Here I have a 2ah and a minus 2ah. Here I have a 6a and a minus 6a. I have a minus a and a plus a. I have a plus 3 and a minus 3. So I'm looking at, I'm going to erase this right here. And I'm going to rewrite this as, this is going to be 6h is what I have left here. And then I have a minus h, so it'll be 5h. And I screwed up here. I should not have combined these. I should have left this as h, a plus h, h plus a plus 3, so that I can cancel that h right there. So now I have 5 over a plus, or ah plus a squared plus this is ah plus a squared plus 3a plus h squared plus ah plus 3h. Oh wait, but this is a limit still. So I've got a plus h, h plus a plus 3, and this is a limit as h is going to 0. So I have 5 over a times a plus 3. Is this a plus h? I missed something here. This is not a plus h. This is a plus 3. So this is a plus 3. And this is, okay, we're going back a little bit. Not that far. So I screwed up here. This is a 3. This is a 3. And this is going to be 5 over a plus 3. And this is going to go to 0. So this is going to be a plus 3. So this is going to be a plus 3 squared. That's it. That's right. That should be right. That was hellish. I'm so sorry.
No, sorry for throwing you off. I was looking at what was on the screen and I thought I was cleaning up, but I just
No, you're good. This is like the messiest. This is the messiest thing. Finding derivatives by hand is the absolute worst, like hands down. So this is f prime of a. So this is the derivative. Yeah, no, shortcuts are going to make your lives so much better. You will never have to do this again in your lives after this section. It's important to understand what's happening, but ouch. Okay, so that was problem 33. All right, let's do a couple of problems from 2.2. Ouch. All right. Yeah, that's right. Shoot. That's what it needs to be. Because that's just with respect to a. Like your answer has an a in it, and you can substitute in whatever you want for a to get your derivative. So, sweet. That's what I needed to get to. Okay. All right. So now we're in 2.2. We're looking at a little bit more of like the derivative as like a graph. I think that problem 3 is a really good problem to do. So we're going to do it. And this is on page 126. So this basically has us matching graphs of a derivative to graphs of the derivative to graphs of the original function. So if you have an idea and a reason for why any of these should be related to their derivative graphs, just go ahead and say like it's a and number 4 or whatever. All right, so a is number 3, or a is number 2. We have 2 different guesses here. So why don't we just kind of sketch out a and take a look at it. So that's not what the graph is going to look like. The graph is going to look something like this. Okay, so when like doing this kind of stuff, I really struggle to do this very visually, so I will make mistakes on occasion, just FYI, but I always look for where the derivative is equal to 0, which is at these min and max points, right? And so from here, it's decreasing. The derivative will be decreasing. I have a negative slope, so I can write that as decreasing, or I can just put a big little negative there. Yes, so the derivative will be negative in that location as well. So I'm going to draw another little cross graph thing here. And we're going to say that this is negative. It's going to be more negative at this point right here. And we know that it hits 0 here and here. So it's going to be more negative when x is very negative. And then it's going to approach 0. So it's going to look something like this. And this is a really klutzy graph, but you know what it is what it is. So it's negative from the 0.2, this infinity to, and it's going to get more negative, right? And then we have this area in here where it is going to be a positive slope. And so it's going to start off being a little positive, and then it's going to get more and more positive, and then it's at its most positive right here, and then it's going to get less and less positive as it approaches 0 again. So it's going to look something like this. So the answer to this is going to end up being graph number 2. And the dealio with this is that this is kind of like a zoomed in version of what function do you think? What function kind of has this like shape? This has a function, a vague shape of like an x cubed function, right? Because x cubed looks something like this. And if you zoom in on this area right here, you'll see that it's going like this around the 0 point. And of course, like this has been like modified in whatever way, but the point is that when you take the derivative, as you'll soon learn, of an x cubed, if you just like take x cubed prime is going to be equal to 3x squared. So you're like moving backwards. So like if you were to take the derivative of a parabola, which is an example of an x squared type function, then you would end up with a derivative that can be represented by an x. So that derivative would be linear. And you're just kind of like moving backwards like that. So if you see something that's very obviously like this kind of looks like an x cubed function, then move backwards and say that I know that I'm looking for a parabola here. And because I'm looking for a parabola, I should not have my stuff tilted out. I should have, should look something a little bit more like this, which was a neat problem. Okay, so we also have a guess for b being 4. Definitely. One easy way to tell is that this is a very linear function, and it's like very choppy, kind of like what we did with that velocity function that we had earlier. And the way that we look at that is that there are constant slopes, which are represented by the straight lines in the derivative graph. So definitely B is going to be 4. So C as 1. Does anyone want to take a crack at that? For these 3? Okay. Well, C is 1. We have a function that looks like this, kind of exaggerated. We have a 0 right here, so we know that whatever function we have at 0, 0, there's going to be there's going to be a point there. And then we know that we have something that is approximately 0, right? So this slope is approximately 0, which means that we're going to be hanging out at approximately 0. I just put this on the wrong. That green dot should not be there where it is on the D graph. I don't know why I did that. This green dot should be here, right here, on 0, 0. So this is going to be this is going to be around 0, like 0-ish, and it's going to be 0-ish right here too. And then we have a area where our derivative is going to be negative. So our derivative is under right here, right? So it's going to be negative. And then here it's going to be positive. And it's going to start off as more positive. And then it's going to be less positive and less positive as it approaches 0. So what does that look like? We have more positive and then less positive, less positive, less positive as it approaches 0. And then for this version down here, we have more negative and then less negative, less negative, less negative as it approaches 0. So exactly right. This is going to be graph number 1. And that leaves us with graph number 3 being for D, and we can just go over that real quick. This is another example of the graph of D looks like an x to the 4th function, and the graph of 3 looks like an x cubed function. So we're again taking a derivative of a graph by kind of walking backwards. So it looks something like this. I can see 3 zeros that I want to mark down. I have a 0 point here, a 0 point here, and a 0 point here. So I'm going to go ahead and put that right on the graph. 0, 0, and 0. So I'll be crossing the x-axis at all of those times. I'll go ahead and mark off where I think that it's positive and negative. I have a very positive area here, and it becomes less positive as it approaches 0, so very positive to less positive. I have a negative portion here. I have a positive portion here. So this is also going to be positive. So that's between the 2nd and 3rd. And it's going to have an inflection point here where it's going to get positive and then it's going to get less positive. And you can kind of tell that because I'm going from a derivative is equal to 0 to a derivative is equal to 0, but I'm staying like technically positive the whole way. So I'm still like in this upper quadrant. So for our negative areas here, we have a negative portion here, and it's that same sort of 0 to 0 type thing, and then we have negative going down to infinity. So it's going to look like that. And that is how we end up with that final graph. Were there any questions about what happened here to make these graphs or to determine what these graphs are? I'm going to take that as a no. All right. let's quick do problem 13. So we have a graph that looks like this, right? So a rechargeable battery is plugged into a charger. The graph shows CT, the percentage of full capacity that the battery reaches with a function of T time elapsed in hours. So this is T, and this is C, and this is percentage of full charge. And so it's like approaching 100% charged, which is what it should. So what is the meaning of the derivative C prime of T? What do you think the derivative means? Yeah, so it's the change in the rate that the phone charges over time. Where is the rate like the fastest? Like when is the phone going to charge the fastest? Exactly. So the phone is charging very quickly here, so we have a very steep slope. And we can kind of see that if we draw ourselves a graph of C prime of T. So it's very positive, and then it approaches 0. So this is going to be T, and this is going to be the rate of change of charge. So I start off, and I'm charging very, very quickly. And then sooner or later, I start to charge much more slowly, and then eventually I'm charging at a near indiscernible rate, and that's essentially when I've hit my 100%. So it's like it's charged, and once I hit that, I can't really do any more charging. But it is charging the fastest the closer it is to 0. It's where it's the steepest. Okay. Usually, I mean, it's been an hour and a half. If you guys have any more questions, like feel free to ask. Usually these things tend to go about an hour. It's really great that you guys had questions and that we were able to talk for like an hour and a half. I do not know when Module 3 will be posted. I don't do any of the posting on Canvas or any of the grading or anything like that. So best person to email would probably be Kasha. So yeah. Yeah, sorry. I'm sorry I don't have a good answer. Any other questions? Okay. Well, I will post a recording to this. It has to render before I do so, and I'll put an announcement in Canvas when the recording for this is posted, and I post these on my YouTube channel. Yeah, which it's just like an easy place to put them, but you know, like comment, subscribe, all that jazz, as a YouTuber would say. But yeah, basically, in addition to having the YouTube channel of this year's stuff, you can also go back and check out my last semester stuff for this class. Last semester, a lot of times people didn't come to these sessions, so there weren't really sessions. But depending on the week, you might be able to check, and there will be a GSG posted, so you could watch through that if you wanted to. If you're not interested, then that's like fine. But it could be an interesting resource if that's something you were interested in. So watch out for my announcement about posting this, and I'll have a link to the channel where you can possibly find more stuff that you can use. All right, if there are no more questions, feel free to leave and have a wonderful evening. If you don't have work tomorrow or anything, then I hope you have a wonderful day, and I hope you have a wonderful day even if you do have work. So yeah, I will see you all next week.